Hello, am I audible?
Yes, sir.
Okay, thanks. Good afternoon. I am Himanshu Mishra, and this week we will be solving some problems which are related to the fundamentals of fluid mechanics as well as the heat transfer. So, we will be applying few concepts from the fluid mechanics and the heat transfer together to find the Nusselt number, heat transfer coefficient, drag coefficient, and hence the total heat transfer rate due to the convection. So we will look some problems related to the external heat convection as well as some few problems from the internal heat convection. And then next week we will be slowly moving to the internal heat convection alone. So let's start today's tutorial. So we will be solving numerical question this tutorial. Numerical questions only. There will be no true and false question, and most of these numerical questions contains a lot of correlation which are very specific to the type of flows like a laminar flow or the turbulent flows or depending upon the value of Prandtl number, Reynolds number and so on. So you don't need to remember all these correlation because if it comes in the exam, probably they will give the correlation to use to find some property or variable and then to find the heat transfer rate. But it is important to know which correlation to use where, in which conditions. So we on most of the questions we will be using those correlations only. So let's start with the first question here. So in the first question, the engine oil at 100 degrees Celsius and a velocity of 0.1 meter per second flows over both surface of a 1 meter long flat plate maintained at 20 degrees Celsius. And we need to determine the velocity. In the first part, we need to determine the velocity and thermal boundary layer thickness at the trailing edge. So we have given so we have a flat plate here. And we have a hydrodynamic as well as thermal boundary layer. And we have given there is an engine oil at free stream temperature of 100 degrees Celsius. And free stream velocity is 0.1 meter per second. So let me list out the properties of engine oil like a density, kinematic viscosity, thermal conductivity and Prandtl number. So at temperature 100 degrees Celsius. So the density is given is actually 864 kg per meter cube. Kinematic viscosity is 86.1 10 to the power minus 6 meter square per second. And thermal conductivity is 0.14 watt per meter Kelvin. And the Prandtl number is 1081. So a few weeks back, we actually did a problem where based on the Prandtl number, we can able to relate which boundary layer is more, like if the hydrodynamic boundary layer is more or the thermal boundary layer is more. So, and the length of the plate is 1 meter. And in the first part, we need to determine the velocity and thermal boundary layer thickness at the trailing edge. So first, we need to check if the boundary layer is turbulent or laminar in nature. So for that, we will be calculating the Reynolds number. over the flat plate. So this is my Reynolds number. I just need to plug the values. And this is my kinematic viscosity. And on calculating, I will get Reynolds number right around 1161, which means that the flow is laminar over a flat plate surface because it is less than critical Reynolds number, which is about 5 to 10 to the power 5. Now, if the flow is laminar, we have a correlation to determine the hydrodynamic boundary layer thickness as well as thermal boundary layer thickness. So for hydrodynamic boundary layer thickness, we will use x root RE. So this is my correlation for the velocity hydrodynamic boundary layer thickness. And x is the length in our case, since we need to determine the velocity thickness at the edge of the plate, that is at L equals 1. So we just put L here. So we just need to plug the values. 1, and we already calculate the Reynolds number here. So on just by calculating, we will get the velocity thickness as 0.147 meter. And for the thermal boundary layer thickness, we can use the Prandtl Prandtl number relation that we used a few weeks back. So the thermal boundary layer can be written in terms of a velocity boundary layer and a Prandtl number. So in order to find the thermal boundary layer, we need to know about the velocity thickness. So we already found the velocity thickness, which is 0.147. And the Prandtl number is 1081. So on calculating, we will have the thermal boundary layer thickness of about 0.014 meter. So this is my thermal boundary layer thickness, and this is my velocity hydrodynamic boundary layer thickness. Now the next part is we need to determine the local heat flux and surface shear stress at the trailing edge. So to determine the local heat flux, we will use the Newton's law of cooling, which is given by this relation, and we need to determine the heat transfer coefficient. And the condition we know is there is a flat plate and there is a laminar flow over the flat plate, which means we can use Nusselt number correlation for the laminar flow over the flat plate. And we know what is the correlation because we solved few questions last week as well. So this is the correlation, and I can write my Nusselt number as HK by L, and we need to find the heat transfer coefficient here. So my heat transfer coefficient will be it's HL by K. So my heat transfer coefficient will be K by L. And we already know the Reynolds and Prandtl number. The thermal conductivity of our oil is 0.14 and the length is 1 meter. Reynolds number was 1161 and my Prandtl number was 1081. So my heat transfer coefficient will be, on solving this relation, I will get about 16.25 watt per meter square Kelvin. So once we got the heat transfer, now it is very easy to find the heat flux, local heat flux. So my surface temperature is 20 degrees Celsius and my free stream temperature is 100 degrees Celsius. So my heat flux will be around 1.3 kilowatt per meter square. So this minus sign indicates that there will be a heat transfer from fluid. So this is my fluid. So there will be heat transfer from fluid to the plate. And positive sign indicates there is a heat transfer from plate to fluid. Because the fluid temperature is higher, 100 degrees Celsius, and the plate temperature is just 20 degrees Celsius. So there will be a heat transfer from fluid to plate, which is indicated by this minus sign. So the next task is to find the surface shear stress at the trailing edge. So for a surface shear stress, last time we used the drag force relation, so we will be using the same relation here. So this was my relation, and shear stress can be given as force per unit area. So my shear stress relation will be this. Now for the laminar flow over the flat plate, I can define my drag coefficient as local drag coefficient as 0.664 Reynolds to the power minus 0.5. So this is my relation, drag coefficient relation for the laminar flow, and when the flow is over the flat surface. So in this case, we can use this relation. So this will be my shear stress over the flat plate for the laminar case. So we just need to put the values here. So density was 864 and my free stream velocity was 0.1. And my Reynolds number was 1161. So on calculating this, we will have shear stress will be 0.0842 Newton per meter square. So this will be my shear stress. Now in the last part, part C, we need to find the total drag force and the heat transfer per unit weight. So until now, we found the local heat transfer and the local shear stress because this is the relation for the local Nusselt number, and this drag coefficient relation is for the local drag. This is actually a local drag coefficient. So for the average, to find the average quantities, for the heat transfer case over the flat plate, when the flow is laminar, we can just write my local heat transfer equals to twice of the average heat transfer. Sorry, my average heat transfer twice of the local heat transfer. And for the average drag coefficient, it will be the same condition. So I can write my average drag coefficient as 1.338 to the power Reynolds number to the power minus zero point 0.5. So we will be using this relation in the shear stress as well as the heat, in the heat transfer relation to find the global quantities. So my drag force will be we just need to put the values. And we will get drag force of around 0.16 Newton per meter. And for the heat transfer, because this is my average or the uh, total heat transfer. I mean, this is my global heat transfer coefficient, which is twice my local heat transfer coefficient for the laminar flat plate case. My local heat transfer coefficient is 16.25. So I will get my heat transfer as 2.6 kilowatt per meter. So this is my total heat transfer, and this is my total drag force, or the global drag force and the global heat transfer. So let me repeat the question here. So here we have given an engine oil at 100 degrees Celsius, and we have given the velocity, free stream velocity, and the surface temperature. We have also given the free stream temperature of the engine oil, and it is said that there is an engine oil which is flows past the flat surface, and the flat surface was 1 meter long. And in the first part, we need to determine the velocity and thermal boundary layer thickness. So this is our rough schematic of the problem. So there will be two kinds of a boundary layer over the flat plate due to the engine oil. This is my engine oil. We first note down all the properties of the engine oil like density, kinematic viscosity, thermal conductivity, as well as the Prandtl number. And then we calculate the Reynolds number to determine whether the velocity boundary layer is laminar or turbulent in nature. So we found that it is laminar in nature. So for the laminar flat plate case, we determine the velocity boundary layer thickness by using this correlation, which is a function of Reynolds number as well as the length of the plate, and we determine the velocity boundary layer thickness. Once we get the boundary layer thickness, we know how to calculate the thermal boundary layer thickness, because in an earlier weeks we already used this expression to compare the thermal boundary layer thickness to the hydrodynamic boundary layer thickness. So this thermal boundary layer thickness is a function of velocity boundary layer thickness as well as the Prandtl number, and we know both the things, so we can easily get the thermal boundary layer thickness. Then in the next part, we have to define the local heat flux and surface shear stress. So We will always be using the Newton's law of cooling to determine the heat flux. But the main question is the heat transfer coefficient. So we need to find the local heat transfer coefficient by using this correlation, which is valid only for the laminar and the flat flow past a flat surface. And we calculate the heat transfer coefficient from this correlation. And then we use the Newton's law of cooling to determine the local heat transfer. Similarly, for the shear stress, local shear stress, we use the drag force relation, and we found that the drag coefficient for the laminar flat surface, we can use this relation, which is the local local drag coefficient relation. Once we found the drag coefficient, we can just substitute in the formula, and we can get the local shear stress. For the global case, in the laminar flat plate surface, the global heat transfer coefficient and the drag coefficient is just a twice of the local ones, and therefore we just multiplied it with 2 and substitute back in the same formula to determine the global properties. So any doubt in this question? Okay, so let's move to the next question. So in the next question, consider steady parallel flow of atmospheric air over a flat plate. The air has a temperature and a free stream velocity of 300 Kelvin and 25 meter per second. Evaluate the boundary layer thickness at distance x equals 1, 10, 100 mm from the leading edge. If a second plate were installed parallel to and at a distance of 3 mm from the first plate, what is the distance from the leading edge at which the boundary layer merger will occur? So first, in the first case, we have only a flat single flat plate, and there is a boundary layer here, and we need to determine the boundary layer thickness at different distance. So let's consider this for the laminar case. Otherwise, you could have checked with the Reynolds number. So for the laminar case, we already find the relation of velocity boundary layer thickness, which is 5x, and the Reynolds number to the power 1 by 2. So I expand my Reynolds number here. So this part is a constant, which means it's proportional to x to the power 0.5. So this part will remain constant always, and we need to put different value of x here to determine the different value of velocity thickness. So let me evaluate this constant part. So my velocity is 25 meter per second, and my kinematic viscosity of air is 15.89 10 to the power 6, and the constant part will be 3.99 10 to the power minus 3. So my velocity boundary layer thickness will be 3.99 10 to the power minus 3 and x to the power 0.5. So I just need to put different value of x. So when the x is 0.001, my boundary layer thickness will be 6. On calculating this, it will be 126 in millimeter. So this is in meter. Similarly, when my x is 0.01 meter, on calculating, I will get thickness of 0.339 millimeter, and at x 0.1 meter, I will get my boundary layer thickness as 1.262 millimeter. So we just use the formula and we just substitute x. That's it. And in the second part, it says that if the second plate were installed parallel to and at a distance of 3 mm from the first plate, what is the distance from the leading edge at which boundary layer merger will occur? So earlier we had only single plate and there was a boundary layer. Now we add a second plate also, and we add this second plate from the distance of 3 millimeter. From the first plate. This is my first plate and this is my second plate. So there will be a boundary layer from here also, and we need to find this distance. Where the merger will occur, will this two boundary layer merge from each other. So this distance we need to find. So here the thickness of a velocity boundary layer is, just from the inspection, it's 1.5 mm from both the sides. So we can use the same relation here. To determine the x. So now we know thickness and we need to determine x here. So we got the relation earlier. So my x will be this is in meter. So my x will be around 141 millimeter. So this is my length, where the horizontal length, where there is a merger of two boundary layers. So in this question, we consider the flow is to be laminar, because even if we consider the flow is to be turbulent, we will be using some different kind of this relation, and where the boundary layer thickness will be proportional to some x 4 to the power 5 or something, or 1 to the 1 ratio 5 or 4 ratio 5, and we will be using. So in spite of that, since in both laminar and turbulent case, the velocity boundary layer thickness is some function of 4 by horizontal distance. So we use a laminar flow just for simplified case, and we use this relation. Anyway, you can just check whether the flow is in laminar or in turbulent case. So we use the laminar case and we use this relation uh, where the velocity boundary layer thickness is given in terms of the horizontal distance and Reynolds number, and we need to find the velocity boundary layer thickness at different horizontal length. And if we just need to plug the different properties of the fluid to do that. And in the second part, we have asked that if the second plate would be exist just 3 mm above the first plate, what will be the horizontal merger length. So in that case, we can able to determine the thickness by inspection. And once we get the thickness, we just calculate the merger length, horizontal merger length. So we just choose this formula in both the problems. For the turbulent case, the method is same. We just need to use a different correlation where the thickness is proportional to x 4 by 5, and all other things, all other methods were same. So any doubt in this problem? I'm audible, right?
Yes, sir.
Okay. So let's move to the next question. So consider the velocity boundary layer profile for a flow over a flat plate to be of the form of u c1 plus c2y. Apply the appropriate boundary conditions, obtain an expression for the velocity profile in terms of boundary layer thickness and phase stream velocity using the integral form of boundary layer momentum equation, and obtain the expression for the boundary layer thickness, local friction coefficient. Express your result in terms of local Reynolds number. So we have a flow past flat surface here. And this is my boundary layer. And the velocity, we have given the velocity profile. C1 plus C2y. So this is my velocity profile. So in the first part, we need to determine the expression for the velocity profile in terms of boundary layer thickness and free stream velocity u infinity. So first, let found the constants C1 and C2. So C1 and C2 can be found by using the appropriate boundary condition. So we will be using two boundary condition at the flat surface here and at the boundary layer thickness. So at flat surface, we have a boundary condition where our velocity at y equals 0. So this is my x, this is my y. This is my y equals 0 and x equals 0 will be 0. And at the boundary layer thickness, I have a boundary condition of u infinity. So let's put this boundary condition in equation 1, which is the velocity profile in terms of constant. So my C1 will be 0 when I apply boundary condition A. When I apply boundary condition B, My C2 will be u infinity by delta. Sorry. So, so my velocity profile will be u infinity by delta by y. So this will be my velocity profile in terms of u infinity and delta. Now we need to determine the boundary layer thickness, which is delta, locally local friction coefficient, which is CF. That's it. So these are the unknown quantities here. So to determine the velocity thickness, we will be using the momentum integral equation. So this you can find in any fluid mechanics textbook in the boundary layer concept. So here from the von Karman relation, you can relate your shear stress to the integral of the velocity of the boundary layer, which is so this is the very general relation. So you have to use this relation to find the all types of boundary layer thickness, velocity thickness, or the drag coefficient. So you just need to put the velocity profile into this equation and to integrate this equation to write your velocity profile in terms of shear stress. So let put our velocity profile. So our velocity profile is A equals u infinity y by delta. So I can write the above equation is and my shear stress here. So my shear stress at the wall can be given as at wall, which is divided by the density. So my velocity gradient at wall will be just differentiate the our velocity profile, whatever the velocity profile we get. So when we differentiate it, we will get u infinity by delta. So we just plug this here. So my mu by rho is just kinematic viscosity here. So this is our relation. So now we put this velocity profile here. So when we take the integral, we will get So I just need to put delta in place of y. So it will be u infinity square 6, and my RHS is kinematic viscosity u infinity by delta. This is my RHS. So I can cancel my this free stream velocity. So this will be the final expression here. Let's say this is equation 2. So we use very general relation to determine the relation between the boundary layer thickness and the other properties. And for our own specific boundary layer profile, which we found out from the boundary condition, we get this relation. So this is very specific relation for only our bound velocity layer boundary velocity layer profile. So let's integrate this equation number 2. So we just need to integrate this. And on simplification, this will be 3.46. Or I can just write in terms of a Reynolds number. So this is my velocity layer thickness, which we derive from the momentum integral equation. Then our next part is to found the local friction coefficient. So we will use the same drag force relation to find the local friction coefficient here. So I'm writing in terms of shear stress, and we know that the shear stress at the wall can be given by Newton's law. Which was delta. So we already found the delta. So I can write my shear stress relation in terms of Reynolds number, because our delta is in terms of Reynolds number and horizontal distance. So I can write my shear stress as now I can use question 3. So just simplifying it. This is my drag friction coefficient. So let me recap the question. So we have given the flat plate boundary layer, and we have given some form of boundary layer profile in terms of constant, and we need to determine the velocity profile in terms of u infinity and delta. So for that, we use the boundary condition to determine. So we use boundary condition at the flat surface and as at the boundary layer thickness. We use two boundary condition and we got the two constants c1 and c2, and we can able to write our velocity layer profile in terms of u infinity and delta. So to determine the uh, velocity thickness, we use the momentum integral equation for the flat plate, which is a very general equation. Once we just need to put any velocity profile into this equation, and it will solve. It will give us the velocity thickness for that specific velocity profile, boundary layer profile. So we put our velocity boundary layer profile into this equation. We integrate it, and it was just a mathematical algebra. And after just using integration and all, we can able to define our velocity boundary layer thickness in terms of Reynolds number and x. And to determine the friction coefficient, we use the drag force relation. We use the Newton's law for determining the shear stress, and we can write the shear stress in terms of Reynolds number and x. And we can just put all the variables in the above equation to determine the average local drag coefficient. So any doubt in this question? So let's move to the next question. So consider a flat plate subject to a parallel flow, top and bottom, and the free stream velocity and temperature is given as 5 meter per second and 20 degrees Celsius. And we need to determine the average convective heat transfer coefficient, convective heat transfer rate, and drag force associated with length 2 meter long, width 2 meter wide flat plate for air flow and surface temperature of 50 degrees Celsius and 80 degrees Celsius. So in both the question we have given the same, we need to find the same thing. Only that in the second part the dimensions are changing and there is a change in the fluid also. So in the first part there is a air flow, and in the second part there is a water flow with change in dimensions. So there is a flat plate. So this is first part. In the first part, there will be a airflow over the flat plate with a velocity of 5 meter per second, and the temperature is 20 degrees Celsius. We have given the length 2 meter and width 2 meter. And the surface temperature is 50. Let's first consider 50 degrees Celsius. And in the second case, we have a water with same velocity and temperature at a phase stream condition, and the length is 0.1 meter, and my width is also 0.1 meter. So let me list the properties of air and water. So my kinematic write for air first. So my kinematic viscosity is 1.669 meters square per second. Prandtl number is 0.706. Thermal conductivity is 26.9, 10 to the power minus 3 watt per meter Kelvin. My density is 1.135 kg per meter cube. So this is my properties of air. Now we need to calculate the Reynolds number to determine whether the flow is in turbulent or laminar regime. My velocity is 5 meter per second with a length of 2 meter, and my kinematic viscosity is 1.669, 10 to the power 5. And my Reynolds I will get my Reynolds number as 5.99, 10 to the power 5, which is more than the critical Reynolds number of 5 into 10 to the power 5, which means there is a transition of a boundary layer into the turbulent. So first there is a laminar boundary layer here, and after some time it becomes turbulent transition. It goes into transition regime. So basically there is a both kind of a boundary layer which exists in this plate. In the first part there is a laminar, and then there will be a transition which make the turbulent boundary layer at the end of the plate. So for this condition, we need to use the drag coefficient and the Nusselt number relation, which is suitable for the mixed condition. So I will write the correlation here for the mixed condition. So the mixed condition is when there is a both kind of boundary layer which can exist over the flat plate condition. So for that, my drag force coefficient correlation can be given as this. So you don't need to remember this formula. Just we need to ensure that we need to use this correlation when there is a mixed condition. over the flat plate. So we already know our Reynolds number, so we just can plug that Reynolds number. So on calculating this, I will get my drag force coefficient as 2.27 10 to the power minus 3. So once I got my drag force coefficient, I will use the same drag force relation to find the overall drag force experienced by the plate. And density was, my velocity is 5. And my area is 2 into 2. And in the question it is given that there is a flow over the top and the bottom part. So there is a flow at the top as well as at the bottom also. So there will be twice drag force which will be acting. So there will be some drag force which is acting on this surface, and there will be drag force acting at the bottom surface also. So the drag force at the top surface will be Fd, and at the bottom surface also it is Fd. So the total drag force will be twice of the drag force. So here I will just multiply it with 2, because we are calculating the drag force at the top as well as at the bottom. So we just need to solve this equation, and we will get the drag force about 0.25 Newton. Now the next task is to find the heat transfer, and for that we need a heat transfer coefficient. And for the heat transfer coefficient, we have to use the Nusselt number correlation, which is valid for the mixed case. So for mixed condition, my average Nusselt number given by this correlation. So we have a Prandtl number of 0.706, and we know our Reynolds number also. So my Nusselt number will be 604. So to find the heat transfer coefficient, I just need to put the values here. So my thermal conductivity of air was 26.9 10 to the power minus 3. And my average heat transfer coefficient is 8.13 watt per meter square Kelvin. So now I can easily find my heat transfer. Now there will be a heat transfer from both the top surface as well as the bottom surface. So it will be twice. my area. My surface temperature is for now 50. My free stream is 20 degrees Celsius. So my heat transfer will be 1950 watt. So when the surface temperature is 80 degrees Celsius, we need to find the properties of the fluid at 80 degrees Celsius, and we need to follow the same procedure. Now let's consider the second case, B. So this was for air case. So for water case, my kinematic viscosity will be 7.291 10 to the power minus 7 meter square per second. My thermal conductivity will be 0.625 watt per meter Kelvin. The Prandtl number is 4.85. And my density is 994 kg per meter cube. So we have a plate with length and width of 0.1 into 0.1 meter. So again we will be calculating the Reynolds number to find whether the flow is laminar or turbulent. So earlier we got the Reynolds number 5.9 10 to the power 5, which is very close to the transition case, where there is a boundary layer which is laminar. It become into the transition jam, and then it converted into the turbulent case. So it happens at less than 5 into 10 to the power 5. It happens nearly at 5 into 10 to the power 5, and it happens more than 5 into 10 to the power 5. So for the water case, we will be finding the Reynolds number here. The kinematic viscosity is 7.29 10 to the power minus 7, which is 6.86 10 to the power 5. So here the conditions are turbulent. Earlier it was a mixed. That means over the flat plate there was a laminar as well as turbulent flow. But now the Reynolds number is very high compared to the critical Reynolds number. The condition over the flat plate is full turbulent. So now we will be using the correlation for the Nusselt number as well as drag coefficient for that, which is applicable only for the turbulent case. So here my drag coefficient can be given by Well, the boundary layer is developing from the from this end, sorry, from this end. So here also it will be a mixed condition actually, because the boundary layer is starting from the x equals 0. The first part of the boundary layer will always be a laminar flow, and only after it will become turbulent. So in this case, the flow will acquire the turbulent regime much early in space. So in earlier case, it is changing into turbulent flow at the end, but now it is changing a bit early because we have a higher Reynolds number flow. But in both the case, we can have both laminar and turbulent case. So it is also a mixed condition actually. So I don't need to remove this part, okay. So my drag coefficient will be around 2.49, 10 to the power minus 3. And I can use the same relation for the Nusselt number as I used here for the mixed condition. So we just need to put the values and we will find the Nusselt number on 1450. My length is 0.1 and my thermal conductivity is 0.625. So my heat transfer coefficient will be 9050 watt per meter square Kelvin. So this will be my final heat transfer, which is 5430 watt. So earlier we got the heat transfer of about 1950 watt, where there is a large plate over which there is a flow of air, and the profile of air is laminar initially, and after at the end of the plate it becomes turbulent. In the second case, we have a very short plate, but there is a flow of water, and the turbulent occurs early in space because the Reynolds number is very higher compared to the air case. So we saw that even there is a very small geometry of the plate here compared to the previous case A. The heat transfer is about 4 times more compared to the B case, even if the plate is very small. And the reason for this is the water, because water has higher heat transfer coefficient. It has higher Nusselt number. So even if the geometry is very low, surface area is very low compared to the previous case A, due to the very high value of heat transfer coefficient and Nusselt number, there will be a higher heat transfer for the water case here. So in this question, we first check, we have given the two conditions, one with air and water and with two geometric condition. And we need to find the drag coefficient, heat transfer coefficient, and the total heat transfer. So we first check with the Reynolds number whether the flow is in laminar or in turbulent regime. So we got the turbulent case in both the case in both the air and water case. So when there will be a boundary layer which is starting from 0, there will be some laminar flow initially and it become to turbulent. So if the Reynolds number is less than 5 times 10 to the power 5, then there will be a laminar flow over the entire region. But otherwise, there will be a mixed condition. There will be some laminar case, then there will be some turbulent case, so we have to use the correlation for the mixed condition. So unless there is a in question there is mentioned of turbulent regime, there sometimes in question they mention that the assume the flow completely in the turbulent regime. So unless that is mentioned, we need to consider the flow always in the as a mixed condition. So for the mixed condition, I introduced the correlation for the Nusselt number as well as for the drag coefficient to find the drag coefficient relation. And we need this drag coefficient and Nusselt number relation to find the heat transfer, drag force, and the shear stress. So we use this relation for both water and air and at different surface temperature. So if the surface temperature changes, it will only change the properties. So we need to check the properties accordingly. So any question in this? Any doubt in this? So let's move to the next question. So unlike the previous question, in this question it is mentioned that the flow is always in turbulent condition. So here we can use the relation correlation for the turbulent case itself, and we don't need to use the correlation which we used earlier in this question, which is valid only for the mixed condition for the laminar plus turbulent case. So in this question, we have given a rectangular fin that is used to cool a motorcycle engine. The fin is 0.15 meter long and at a temperature of 250 degrees Celsius, while the motorcycle is moving at 80 km per hour in air or at 27 degrees Celsius. The air is in parallel flow over the both surface of the fin, and turbulent flow condition may be assumed to exist through. What is the rate of heat removal per unit weight? So we need to determine the heat transfer rate, which can be given from the Newton's law of cooling. And as the standard procedure, we need to find the heat transfer coefficient. And it is given in the question that the air is in parallel flow over the both surface. So that means we have a fin air and there will be a flow of air at the both surfaces. So there will be heat transfer from both surfaces. So there will be a twice of heat transfer. So for turbulent case only. So here according to the question we have given only turbulent case. There is no laminar profile. So for that the average Nusselt number will be this. So we just need to find put the value of the Nusselt number and Prandtl number here. So this is my velocity. This is my length. So I'm expanding the Reynolds number. And my kinematic viscosity of air is 27.85 10 to the power 6. And my Prandtl number of air is around 0.7 that we have seen in the last question where we took air's Prandtl number equals to 0.7. So on calculating this, we will get the Nusselt number around 378. And this will be my heat transfer coefficient. The thermal conductivity is 0.0346. So my heat transfer coefficient will be 87 watt per meter square Kelvin. So now I can use my Newton's law of relation to find the heat transfer. So we need to determine the heat transfer per unit width. My length is 0.15. So my heat transfer per unit width will be 5826 watt per meter. So in this question we have given there is a airflow over a flat plate or a rectangular plane, and since there is a flow of air at both the surfaces, we need to find the heat transfer, assuming that the condition is turbulent, the flow is in turbulent condition. So we use the Nusselt number, which is valid only for the turbulent case, not for the mixed case here. And we use the standard procedure, find the Nusselt number and then find the heat transfer coefficient. And then from there we just find the heat transfer. So any doubt in this question? So let's move to the next question here. So in this question, for the flow of a liquid metal through a circular tube, the velocity and temperature profiles at a particular axial location may be approximated as being uniform and parabolic. So we have given the velocity profile as well as turbulent temperature profile. So here C1 and C2 are constant and we need to find the Nusselt number at this location. So we have given that velocity profile C1 and we have given the temperature profile C2 1 minus R by R naught square. And to determine the Nusselt number, we need to first determine the heat transfer coefficient. So basically we are going opposite direction. So in the previous problem we found the Nusselt number by using the various correlation depending upon the flow conditions. Then after we got the Nusselt number, we found the heat transfer coefficient. Here we first found the heat transfer coefficient, and then whatever we got, we will from that relation we will find the Nusselt number. So my heat transfer coefficient will be given as in terms of heat flux and temperature difference. So here Ts is my surface temperature and Tm is my mean temperature. And this is my heat flux. So we need to find the mean temperature here because we have given the temperature profile, so we can obtain the mean temperature from our temperature profile. So we know that the mean temperature can be written as So basically, we just need to put our temperature profile and velocity profile in this integral. So my velocity profile is C1 and my temperature profile is Ts plus C2 R by R naught square RdR. So on integrating, we'll get R square by 2 C2 R square by 2. This become R cube R4. Let's say it's my R naught. So we just need to plug this value here. So it will be so on simplification, I will get my mean temperature as in terms of Ts. Now we can use Fourier's law to determine the heat flux. So this is my equation 1. So this is my expression for the mean temperature. So the heat flux will be given as this from the Fourier's law, and by differentiating this temperature profile at R equals to R naught, my heat flux will be R naught at R equals R naught. So my heat flux will be here. So now I can use this relation here. So we got the heat flux and we got the mean temperature profile. We just need to put here to find the heat transfer coefficient. So my heat transfer coefficient is 4K R naught C1. So this is my heat transfer coefficient, and to find the Nusselt number, we use, and my heat transfer coefficient is 4K UM R naught by C1 multiplied by R naught by K. So it will be 4 UM by C1. So this is my Nusselt number. This is my heat transfer coefficient, and this is my mean temperature profile. So here in this question, we have given that there is a flow of a liquid matter, and we have given the velocity and temperature profile of that liquid matter, and we asked to find the Nusselt number. So we first use the Newton's law relation to find the heat transfer coefficient, which can be written in terms of heat flux, surface temperature, and mean temperature. But we don't know about heat flux and mean temperature. So we found mean temperature and heat flux first. To find the mean temperature, we use the general relation for the mean temperature. We integrate our velocity and temperature profile to find the mean temperature here. And to find the heat flux, we use the Fourier's law at R equals to R naught. Once we got these two quantities, we just put back into the Newton's law of relation to find the heat transfer coefficient. And from the heat transfer coefficient, we can always point out the Nusselt number. So this heat transfer coefficient and Nusselt number is for the given velocity and temperature profile. So any doubt here? We can even further simplify this temperature relation. We can find the mean velocity profile also. The mean velocity profile can be written as 0 URDR. So by using this integral, we can find the mean velocity expression. We put our mean velocity expression here. So in that way, we can write our heat transfer coefficient in terms of only thermal conductivity and this geometric property of our system. We can just omit U and C1. We just, for U1, you just need to take this integral if you want. So
can you just explain how that Tm initially, that how the expression you have got of Tm?
It is just average that we got for the heat transfer condition. So for the heat transfer case, we use the Newton's law of cooling here to find the average of the heat transfer relation, which was 1 by A H dA. So for the velocity, we use the mass conservation, where we equate this mean mass conservation equation into the change in mass conservation equation, and we get the velocity, average velocity UM in the same thing. For the temperature, we use the energy condition, the mean energy condition, which is equal to the variable energy condition here, and we can able to write this mean temperature profile, average temperature profile here. So this temperature profile is for very general case. Uh, it can be used for arbitrarily various kinds of temperature and velocity profile.
Okay.
Yeah. So again, in the next question, we will be using this temperature and the velocity profile to found out the heat transfer coefficient. So in the next question, we have given the velocity and temperature profile for laminar flow, and of a radius of 10 mm, we have given the velocity and temperature profile, and we need to determine the mean temperature at this axial location. So we will be solving the same expression here. So this is my mean temperature. So if we solve for the mean, so we already have a temperature and velocity profile given. So if we found the mean temperature here, it will be in terms of mean velocity and the geometric property like radius, like before here. So to solve for the mean velocity, we can solve for the mean velocity to remove this variable here. So this is my mean velocity given. So I just need to put the velocity profile expression here. I can simplify this expression as so I just put r square in the numerator and denominator, so I can write like this. So I can now directly differentiate here. Which is r naught so now I can integrate this. So this will be changed because it will be 1 now, because I'm writing like this. So at the end, at r naught, it will be r naught by r naught. It will be just 1. So my upper limit will be 1 now. So solving this, (0.05 meter per second). So my mean velocity is 0.05 meter per second. So similarly, we can take the mean of the temperature. And just directly put the values. So this is my velocity profile. This is my temperature profile. So if I introduce R naught square in the numerator, I have to introduce R naught square in denominator also. And my is 0.05. So now I need to integrate over 1 to 0. So it will be 0.1. So just evaluating this integral. So we write R by R naught as, let's say, A. It will be just 0.1, 1 by A square, 3448 plus 75 A square to the power 4 A dA. So we just need to evaluate this integral here. And when we evaluate the integral, we will get the mean temperature is 367 Kelvin. So in this question, we have given the velocity and temperature profile, and we asked to obtain the mean temperature. So we just use the relation for the mean temperature here. So first we solve for the mean velocity here, um, and we got the mean velocity 0.05, and the mean temperature, we just substitute the velocity and temperature profile in, let's say, equation 1 to get the mean temperature. So any doubt in this one?
No, sir.
Okay, so let's stop here. So next week we will be solving some problems related to the internal heat convection. So we will be solving problems which are related to two concepts, like constant temperature case, where there is a constant temperature over the surface of a pipe, and for the constant heat flux case, where there is a constant heat flux over the surface of the pipe. And for these two different conditions, we will be solving questions. We will be writing some Nusselt number and drag coefficient relation for these specific cases, and we will be doing the same procedure, finding the heat transfer coefficient and the heat transfer then. And then we will move to probably the heat exchanger problem, which are just advanced version of the internal heat transfer convection. So today we look some heat convection problems which are related to the external flow as well as some internal flow. So for today's question, basically we solve two types of problems where we use the correlation, like Nusselt number correlation or the drag coefficient correlation, to find the heat transfer and heat transfer coefficient, drag force, and shear stress. This correlation depends on the specific flow condition, like if the flow is in laminar or in turbulent flow. In the second type of problem, we just solve for the velocity and temperature profile. We obtain the mean temperature, mean velocity, and the distance of the hydrodynamic boundary layer. So basically, these are two types of problems that you can encounter in the external uh, heat convection concept. So yeah, if you have any doubt, you can just ask, or you can just revise by watching video. I will upload this in YouTube.
Okay, sir.
Okay, that's it for today.